So imagine a falling rock. And once again, like I said, that's the only rock I could find a good picture of. The distance y as it is fallen after t seconds can be modeled by y equals 16t squared. What is the average speed over the first 2 seconds? So the speed is, what is the speed as t goes from equals 0 to t equals 2? Okay, that would be that. Find the average. Okay, so the average speed would be 16 times 2 squared minus 16 times 0 squared over 2 minus 0. Right? That would be the average speed. That's your average. You're going from this point to that point. What's the average between the two of them? What's your average slope between the two? Speed is rate of change. Slope is rate of change. 2 squared is 4. 16 times 4 is 64. 64 divided by 2 is 32. Is that right? Did I do my arithmetic correctly in my head? Okay. So over the first 2 seconds, that's the average speed. Is that exactly how fast he's going at 2 seconds? No. It's the average of the two, because at time 0, how fast is he dropping? 0. There's acceleration, but there's no velocity, because it's gravity. It's acceleration is making him move. Okay, but there's no velocity. So I go from 0 to something else. I have an average in there, but I don't have the exact. This is how things have been for a long time. Now, here's what I would like you to do. Answer the rest of those questions. What is the average speed between the first and second second? What is the average speed between 1.5 and 2 seconds? What is the average speed between 1.75 and 2 seconds? Take a minute, work those out. Get a calculator, do it on that, not in your head. Try this. This is what? Y equals 16t squared. That's its position. That's where it is. How do you find the average speed? Change in distance over change in time. Distance over time. That's what that is. Change in distance over change in time. So that's what you worked out. Okay. So average speed between first and second seconds. What do we get? 48. And this is what? Feet per second, right? Yeah, I think it's feet per second. Yeah. What is the average speed between 1.5 and 2? 36? 56, thank you. 56. And the average speed between 1.5, 1 3/4 and 2? 60. Do you see what's going on here? Now, our time interval. So we have starts here and then falls, and after 2 seconds, we're here. So we figured out the average speed of that whole distance on the first one. And then we said, okay, we want to get, what is the average speed over half of that distance? What is the average speed over half of that distance? Over half of that distance. If we were to keep going, what would we be doing? We'd be taking half and we'd be doing half and doing half and half. What is that distance approaching? No. It's approaching the point of 2. But what is the distance approaching? It's approaching 0. I'm trying to get it down to a 0 distance. That's what we're going towards here. The distance between these 2 points, going from here to here, the distance between those 2 points is getting a half each time, which means that my distance between them is approaching 0. If my distance between the 2 points is 0, that means it's what's going on exactly at 2 seconds. This is what began calculus. Rather than using averages, how can we calculate the instantaneous? You got to remember, this is the 1600s, 1700s. I think it was 1600s when you did this. It's not like you had a radar gun you could point at the wagon coming down the road. You had to figure out an equation for where it is, and then figure out how fast it's going from there, and find the stuff that went from there. This is what calculus was all about, finding the instantaneous rate of change, rather than an average rate of change. Instead of what's going on between here and here, what's going on right now. What's going on right now. That is what calculus is all about. Calculus is computing rate of change at an instantaneous moment. That's what began this whole thing. And from there, it has grown and grown and grown into so many applications, it's not even funny. But that's how it began. Motion of objects, specifically falling objects, and how can we figure out the instantaneous rate of change? How can we do that? So if we're approaching a particular value, what is that? What are we doing? We're taking a limit. So limits are important from the standpoint of that's where it all begins. It's the definition of a limit. We're taking a limit as x approaches a particular value. As we approach a particular value, that's what we're doing. Okay? So graphically, what we're talking about here, average rate of change, is the slope of the secant line. Slope of the secant line. Secant line, remember secant in circles? The line across the circle. The secant line is a line that connects up 2 points. The instantaneous rate of change, however, is the slope of the tangent line. It's what's going on at that point. What is the slope at that point? Okay. So, for example, can you draw a picture of a secant line of the curve y equals x squared from the origin to x equals 2? Let's slide this up. So I'm going to go from here to x equals 2. That's that point there. I'm going to, boom. That's the secant line. Okay. So that's the secant line. The secant line connects 2 points. Okay. And the secant line continues on out. And continues on out. But that's the secant line. The tangent line, on the other hand, is the slope at that point. It's the slope that's going on right here. It's the slope that's going on right there at that point. Remember, if we zoom in close enough on a curve, what do you see? A flat line. So if I have a curve and I have a tangent line, if I zoom in close enough, what are they? They are the same thing. So the slope of that tangent line is the slope of the curve at the point of tangency. Because if you zoom in close enough, the slope of the line and the slope of the curve are exactly the same thing. That means the rate of change of the curve is equal to the rate of change of the tangent line at that point. So that parabola actually describes the motion going on the falling object. Okay. If we graph y equals 16t squared, what do we have? We have a parabola. These are all the slopes of the secant lines connecting those 2 points, connecting 0 and 2, connecting where x is 1 and x is 2, connecting where x is 1.5 and y and x is 2, connecting those secant lines. If we zoom in close enough, we have the tangent line. The curve of the tangent line is the same as the curve of this line. Slope measures change. This is the position. The slope is the change in position. If we find the slope of this at a point, we have found what the change in position is at that particular moment. We have found the speed at that particular time. That's what we're doing here. We're not finding the average. We're going to find out what it is exactly there. Exactly at that time. Okay, it's not like we're going to stopwatch, start, stop. Okay, they traveled 10 feet. This is how long it took them to go 10 feet. We'll know exactly what it is when they cross the finish line. Now we have technology that will do that stuff for us. 300 some odd years ago, they didn't have the technology to do that. This is what they did. This is the big breakthrough, being able to do this and then make those applications even more. Had to invent a brand new realm of mathematics to be able to do that. That's what Newton did. That's one of the things that everybody was all hot and bothered about him doing, is all the physics, but the math to support the physics. He invented the mathematics that did not exist to support his work. We know when calculus was invented. And this is why it was the same. Okay. So, the slope of a curve, f of x, at a point, P, A, f of A, is the number. The slope at a particular point. So if I have that curve, and we're actually going to be doing this here in a second, the slope at that particular value is the limit as h approaches 0 of f of A plus h minus f of A, all divided by h, as h approaches 0. So what were we doing? We were taking the points and moving them closer and closer to 0. Right? We were taking, that's what I was talking about. H is the distance between those 2 points. Because our denominator is A plus H minus A. If you go back to change in Y over change in X, that's what this works. F of A plus H minus F of A over A plus H minus A. And what does A plus H minus A over simplify down to? H. This is the distance, that's the distance between those 2 points. Point A and point A plus H. As H gets smaller, those 2 points get closer together. So instead of a secant line connecting 2 points, as H goes to 0, I get 2 1 points. And it says, very key words, provided the limit exists. So you have to be able to do that. There are times when the limits don't exist. And we will actually discuss that a lot more in the next chapter. This is called the difference quotient, and used to find the slope of a tangent line to a curve at a point. You will need to know that formula. In fact, I'm going to write the formula down over here so I don't forget it as we're doing today's work. And this is where your algebraic skills are going to come in handy. Okay? This is where your algebraic skills come in handy. If f of t equals 16t squared, ooh, does that remind you of anything? That is the distance where the rock was at as he was falling. Okay? At a particular time. And we want to find out what it was at x equals 2. We want to know the instantaneous speed after 2 seconds. So we're standing there, 1001, 1002. He's right here. We want to know how fast he is as he's falling past us. Headed towards sure danger until we get to the next wheel. Right? Because he's not going to die. We're not going to kill him. So we want to take the limit as h approaches 0 of 16 times 2 plus h squared minus 16 times 2 squared over h as h approaches 0. Yeah, everybody loosen up a little bit, because here's when the fun starts. Okay, here's your algebra skills coming in handy. First thing, factor out the 16, pull out the 16. It is 16 times the limit as h approaches 0 of 2 plus h quantity squared minus 2 quantity squared all over h. Because if I have a constant times a function, the limit of a constant times a function is the constant times the limit of the function. So I can factor out the 16 and pull it out front and ignore it till I'm done. (16) times the limit as h approaches 0 of 2 plus h squared. That's 4 plus 4h plus h squared minus 4 all over h, which is 16 times the limit as h approaches 0. What happens to my 4's? Bye-bye. 4 minus 4, nada. 4h plus h squared all over h. And you're going, oh crap, Mr. Orris, I still have h in my denominator. I can't put 0 in there. Well, I can factor and cancel. I have an h in every term. I can cancel an h out of every term. Told you your algebra skill is going to be awesome. This h, and one of those cancels. So I now have 16 times the limit as h approaches 0 of 4 plus h. Can I put in 0 for h now? Yeah. So that is 16 times 4, which is 64. So he was traveling at 64 feet per second after 2 seconds. That was his exact speed at that time. And if you have a falling object dropping without any air resistance, that's how fast you will be traveling, irregardless of this. No, you have to be able to show me the work. What? No, you can't because 2 into t. If this was 3 seconds, it would not be 16 times 3 squared. That's where it is. It's not. This is okay. This is the only time where and how fast it's moving have the same numerical value. That and it's 0. These are the only 2 times when it stopped at the very beginning. When time 0, speed is 0, and time 2, speed is 64 feet per second, distance is 64 feet. It's the only time they are the same value. It's the only time it actually happens that way. It never happens that way any other time. It's just one of those things. If time was 3, this would not match the distance. The speed would not be the same place. And at 1 second, they're not the same. Okay. Okay. Now, a nice demonstration. There we go. Okay. So if I look at this, here's what's going on. They've laid it all out here, all the equations and stuff. Here's my original function. A is the point that I am, is my point of tangency that I'm looking for. And h at this point goes between 2 and 8. So what I've got here is I've got now a secant line, and I'm trying to find the tangent line. Same concept we just did, only graphically. I'm going to see if I can make it a little bigger. There, that helps. Slide this over. Okay. So I have point A, and I'll make this a little bit nicer point. Okay, at point 2. There we go. So here's what I want to do. This is the point of tangency. Think about this as x, or this is A, this is point A. This is A plus h. So if I take the limit as h goes towards 0, right now they are 2 units apart from each other. If I make it smaller, so I'm taking this thing here, and I'm making the distance between these 2 points get smaller and smaller. Notice what's going on here. Eventually, stop that.
Oh, no.
There we go. So if I do this, I pass through it. Why is it doing that? Here, I'll do it on the computer. It'll work better with the mouse.
Hey.
So, okay. So if I do this, notice as I approach, as the 2 points get closer and closer together, the distance gets closer and closer to 0. Now, right at 0, it goes away because it's undefined at 0. But when I'm really, 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 really close, this is my tangent line. if I were to zoom in, it's almost the same. I don't think I can get, no, I can't get any closer than 1/10 away. But the slope of the two, I mean, look at them. They're essentially identical. They're essentially, I know, like I said, I don't know. Will that let me do that? Oh, yeah.
Well, that's a 0.01.
If I move in really, really close, you can't tell the difference between the tangent line and the curve. And if I got really, really close, okay, you can't tell the difference between the two. Okay, now, if I were to zoom out, but where is that tangent line accurate at? It's only the same at that point. If the point is farther away, it doesn't do me any good. Okay, so we will be using tangent lines to evaluate curvature curved functions, use a straight line, but you can see it only works up close. But taking the limit as the distance approaches 0, the slope of that curve and the slope of the line are the same slope. So we know exactly what the slope of the curve is by finding the slope of the line tangent to it at that point. That's what we're doing here. We can find the slope of the curve. We can find the slope of this curve at a particular value. Here's something that's changing constantly, but we can find it at one particular value along the way. That's what we're doing here. Okay, we can find it at one particular place. And let's go back to that. Okay. Now, the normal line, and I talked about the normal line briefly. The normal line is the line perpendicular to the tangent at that point. Example number 3. Find the equation of the tangent line and the normal line for the curve y equals 1 over x minus 2 at x equals 3. Okay? What do you need to find a line? There are 3 things you need to write the equation of a line. 3 things. Slope and a point, x coordinate, y coordinate. What do we already have? X coordinate. We have an x coordinate. X is 3. How do I find our y coordinate? Because that's a lot easier to find than the slope. Plug it into the original equation. So when x is 3, y is 1. There's my point. Now I need my slope. F of A plus H minus F of A all over H. A is 3, F is 1 over X minus 2. So I have the limit as 1, as H approaches 0 of 1 over 3 plus H over 2 minus 1 over 3 minus 2 all over H. Can I put in 0? No, I don't want to put in 0. I need to do some algebraic manipulation. Once again, you're ready to flex your algebra muscles because we're going to do it. Yes.
Where the 1 over the 3 plus H minus 2 come from? Like,
F of A plus H. A is what? A is 3. 3 plus H. So it's 1 over where X is equal to 3 plus H. Okay. So, first step, start to simplify. Limit as H approaches 0 of 1 over 1 plus H minus 1 all over H. Okay. Now, this is, pay close attention. When you have a compound fraction, we don't like compound fractions. How do you get rid of a compound fraction? And using your eraser does not count. Okay. What you do is you multiply by the common denominator. What you want to do is you want to get rid of the compound fraction. I want to make this no fractions on top. So in my numerator, which is the only place I have actually a fraction in a fraction, I want to get rid of this. So my denominator here, my common denominator in my numerator portion is 1 plus h. So I multiply times 1 plus h. And if I do that to the numerator of the whole fraction, I need to do that to the denominator. So I'm multiplying actually by 1. Because 1 plus h divided by 1 plus h is 1. Multiplying by 1 will not change the value of my fraction. It will still strictly change its appearance, but not its value. Okay, that's why we do that. Multiply by something over itself. Because that's multiplied by 1. Multiplying by 1 does not change the value. All we're doing is changing its appearance, but not its value. So that equals the limit as h approaches 0. 1 over 1 plus h times 1 plus h is 1. Minus 1 times 1 plus h is 1 plus h. All over, and do not FOIL it out. Do not FOIL it out. Trust me, I know what I speak of. I've been here before. Okay. I still can't let h be 0, although I kind of can now, but there's something else you want to do first. Okay. What is my numerator? What happens here? If I distribute the negative 1, the negative, what do I get? 1 and the negative 1 cancels. What do I have left in here? If I distribute and combine like terms, I get what? I get the limit as h approaches 0 of negative h over h times 1 plus h. Distribute the negative, combine like terms, I get negative h in my numerator. And look what happens here. These reduce, that becomes a 1 on top. So I have the limit as h approaches 0 of negative 1 over 1 plus h, which is negative 1. I can now, even though I have h in my denominator, I can let that h be 0. I couldn't before because I had 0 times 1 plus 0, which is still 0, and we're never allowed to have 0 in our denominators. But I can do it now, and I did, and I get negative 1. So the slope of my line is negative 1. This is the slope of the tangent line. Okay. Okay, so you'll notice I have an incomplete formula up there for equation of a line. This is the one that I love. This is the one that works all the time. What's the xy coordinate? 3 and what? 1? 3, 1. So the x coordinate's 3, y coordinate's 1, and it's the same for both of them because they both pass through the same point. The only difference is the slope. What is the slope of the tangent line? Negative 1. That's what we spent all that time finding, was that. Okay. What is the slope of the normal line? Positive 1, because they are perpendicular, which means it's the opposite inverse. Change the sign, put 1 over it. There we go. It will not always be this difficult to compute the slope of the tangent line. We will be writing lots and lots of equations of tangent lines and lots, but not lots and lots, of the normal line. Several homework problems, test questions, AP test questions involve doing that. Finding the slope will not always be this difficult. Sometimes it will be harder. Usually it'll be easier though. Okay, but this is it. You're going to do this. Finding the x-coordinate's easy, right? Because you're told the x-coordinate. Finding the y-coordinate's easy because you just plug the x-coordinate in the original function. The slope is the hard part. We're going to be finding the slope in new and wonderful ways as we progress throughout this textbook. But we're going to be doing this an awful lot. The ways of finding the slope will change over time. Okay. Yes?
Can you explain why the normal is not negative one?
They're perpendicular. Perpendicular opposite, so you change the sign, flip it over. Okay. Okay, find the slope of the curve at x equals a, and describe what happens to the tangent at x equals a as x changes for the function y equals 2x squared plus 3x. So here's what it's saying. It's saying do this, only instead of a particular value for a, you use a itself. So instead of like what we did on the last one, 3 plus h and 3, it will be a plus h and a. So we want to find the limit as h approaches 0 of 2 times a plus h squared plus 3 times a plus h minus 2 times a squared plus 3a all over h. That's what that question is asking you to do. Instead of at a particular value a, you're doing it at a generic value a. So you're going to get a generic formula for the slope. Please take a couple of moments and do the algebraic manipulations. All right, here we go. This is the limit as h approaches 0 of 2 times a squared plus 2ah plus h squared plus 3a plus 3h minus 2a squared minus 3a all over h, which is the limit as h approaches 0 of 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 2a squared minus 3a all over h. 2a squared cancels with 2a squared. 3a cancels with 3a. So my a's are gone. And then my h's can cancel. I have one h in the denominator. That one's gone. That reduces by a power of 1. And that one's gone. So I have the limit as h approaches 0 of 4a plus 2h plus 3, which is 4a plus 3. That is the slope of my equation. That is the slope of the line tangent to 2x squared plus 3x at any particular value of a. So, when x is 5, the slope of the tangent line to this when x is 5 is 23. The slope of the tangent line to this when x is negative 2 is negative 2 times negative 8, negative 5, thank you. Sorry, my arithmetic wasn't going. But this is the slope at any particular value. I can now find the slope of the tangent line to any point by plugging it into a formula rather than having to do that limit thing all over again and again and again. That's what this is. This is the formula for the slope to this at any particular value a. That's what that is. So as my x-coordinate changes, it's x equals a. I change my value of a. I change the value of the slope accordingly. This is a parabola. It makes sense when I have a parabola. 0 and it looks something like this, I believe. So I've got a tangent line here, and I've got a tangent line here, and I've got a tangent line here. All the slopes for tangent lines are different depending upon where I am finding the tangent line at. All of the slopes of this are different depending on where I'm at. If this is an equation that describes position, this is the equation that describes velocity. So if you think about the falling rock, it was a quadratic. If we did the same thing and found the equation that went with that at point A, point A, this would be the equation of the velocity of the rock that is falling. Okay? And that's it.